Yes, it's everything clear now.
Okay, please start.
It's clear.
Yeah, it's clear.
Okay, thank you very much. Hi everyone. Good afternoon or good evening, depending on your time zone. Today I'm presenting my project about the oxidative coupling base reaction for the indirect spectrophotometric determination of paracetamol in a drug formula. Paracetamol, as you know, it's a mild pain relief and fever reduce medical. It has been generally used for more than 60 years. Um, the, the expected mechanism for the action is still not fully understood. Therefore, there are a lot of research has been done in this particular drug. It's highly recommended for the adults and for the children's above 18 years old, and also it has been given for the youngest children and even the infant. It's the recommended dose for it is between 500 to 1,000 milligram each 4 hours as necessary. However, it is unsafe drugs because it most probably like a high dose of it harm the livers. Therefore, the determination of the concentration of the paracetamol is very important, especially in the like drug companies. There are many numbers of analytical approach has been investigated to determine the paracetamols in pure form or in on the formulas, and also in biological fluids such as the blood or urine. These methods like such as the researchers before they use chromatography or the flow injections or even using the voltammetry. However, today I'm talking about like a new method that's using a spectrophotometric method for determination of paracetamols in drug formula and in pure form. Our method is depending on hydrolysis of paracetamol. Like first will be hydrolyze the paracetamols in acid media to form a para-amino phenol, and then the para-aminophenol it will be oxidized by the dissolving oxygen to form hydroquinones. And then after that, we coupling this hydroquinone or the resulting hydroquinone with different reagent. Here also using, for example, the uh, Methyldopa solution. Like Methyldopa is like type of amino acid, and then it will be reacted with the resulting hydroquinone to form a phenol called indophenol dye. This dye they have a color, and then you can measure the color to give us some information about the concentration of paracetamols in any like in formula or in pure or even in fluid liquid or biological liquid. This figure show the spectra, the absorbance spectra of 100 ppm of hydrated paracetamols. That means after you hydrated the paracetamols and the paracetamol with methyl dopa in acid media to form a dye, and then this is the spectrum of the dye by using the spectrophotometric device to like looking for the applicants of this method and how we can apply this method and how is the accuracy and the precision of this method. You have to study some like parameters. One of these parameters is the indophenol's dye stability. As we show in the literature, most of the literature has been mentioned that the absorbance of the endophenols dye is unstable. Therefore, they're adding a lot of materials that can stabilize the dye or the produced dye, such as using, for example, use copper. Uh, The copper can react with these type of dyes to make it more stable. However, in our study, we measured the stability for long time, and we found that the produced dye is very stable for a long time. Therefore, we don't need to add any other like compound that help to stabilize the dye. The second parameters we studied is the effect of the temperature. As you know, we're making like chemical reaction between two compounds. Therefore, we have to looking for the effect of the temperature for this reaction. As we see in the figures, like in the right, um, the absorbance of the paracetamols with the methyldopa, it's increasing with increasing the temperature until it's under the temperature is 35, and then after that the absorbance will decrease dramatically because maybe it's like they damage the dye because of the heat. uh, and then we study the stability of the dye in like in the room temperature. We found that in the room temperature, the produced dye is very stable for like more than 2 hours, which is very enough to do all the measurement. Also, we studied the order of the addition because we only have two additions, like two compound only, like adding the hydrolysis of paracetamols with the methyl dopa in the presence of a base that give me a color directly. Therefore, we don't have actually much order reaction. Therefore, like we just like changing the compound instead of each other, and we don't found any effect of the order of the reaction. Therefore, we're moving directly to study the effect of the base. As you know, there are different type of base, and you study the effect of different type of base. So most of like it's like weak base or strong base, and we found the strong base give us uh, more or better results. Therefore, we're using the NaOH, sodium hydroxide as a base, and then we moving to study the amount of the base that we add. Therefore, as you see in the table on the right, we adding different uh, volumes of NaOH, and then you measure the absorbance for 100 microgram per milliliters of paracetamol, and then we found that adding adding 1 milliliters of 4 molar of NaOH give the absorbance that therefore that's recommended for all sequence experiments. And then also we study the effect of the concentration of methyl dopa. As we know, like we don't know exactly how much we need from each of the compound for the action. Usually, therefore, usually we adding more concentration of methyl dopa or any reagent that with the reaction to cover all the amount of paracetamols that need to calculate or determine the concentration of it. Therefore, we adding different concentration, different amount of 1 to 10 minus 3 molars of methyl dopa, and then also we measure the absorbance for 100 microgram per milliliters of paracetamols, and we found that adding 2.5 milliliters of methyl dopa give us the more like give us the more color and intensity for produced dye. Therefore, we depend on this amount for the following addition. As you know, like the calibration curve, here we study the calibration curve. The major reason for studying the calibration curve to know the limitation of our experiment. That's mean we have to detect the range of the determination. That's mean we have to start, like for example, we said, for example, this experiment, we say that the range of the concentration between 10 to 100 microgram per milliliters. That's mean the less concentration can detect by this method is 10 ppm, and the highest concentration can be detected at 1000 ppm. That means any concentration less or more than this range, it will be hard to detect, or there are or inaccurate result we will get. Therefore, the range of this experiment, it will be in this range, and higher of this it will be has a defect or negatively draft from the calibration curve. And then also the calibration curve give us very straight line. That means our experiment is very accurate and that have high precision. Also, we have to study the stoichiometrics and the mechanism of the reaction. That's mean we don't know actually when you start, we don't know how much, for example, from A reacted with the B, like how much mole of A react with how much moles of B. Therefore, we do this stoichiometric titration, and to know it's usually do by two methods. This one of them is called joke method, and the other one is called mole ratio method. That's mean adding different moles of the compound and study the color intensity. And then after that, we found it's the reaction between the paracetamol or hydrated paracetamols and methyldopa. It's 1 to 1, as we saw also in on the mechanism. The effect of interferences, as you know, in the drug formula, usually they adding a lot of compound, and we have to make sure this compound, such as, for example, glucose or arabic acacia or starch or lactose, usually adding for the drugs to make it more acceptable, especially for the children. Therefore, we have to make sure these all our compound doesn't affect our procedure. Therefore, we study the effect of the interferences, and we found almost most of these compound or additive compound doesn't affect our experiments. And also we study the effect of surfactant. The surfactant is like a chemical compound that increase the solubility of the organic compound in the solution. Therefore, we add this compound to increase the solubility of the dye. Uh, it has been used from a long time ago to improve the spectrophotometric method, but actually with our result, we don't see any effect for the cation or anions or even the natural surfactant, where therefore we don't depend on the addition of these. And then after the end of this section, when we talk about the evaluation of analytical data, actually we try to evaluate our experiment and compare this experiment with other uh, method has been used, or for standard method has been used from like British pharmacopoeia, for example, or British companies or American uh, uh, standard methods. Therefore, try we try to calculate a lot of parameters that give us information about the accuracy and the precision of our experiment, and we calculate, for example, the error and the relative error, and also we calculate the standard deviation and relative standard deviation, and all of these result that we got, as you show in these ones, like all this relate number that show us the, for example, the recovery and the relative standard deviation. All this give like indicate that our experiment is very accurate, and that has high precision. That's mean it can repeat the experiment and get almost similar results. Therefore, we can depend in our method determine the concentration of paracetamols in different formula. In the conclusion, we developed a high and simple and accurate and sensitive indirect spectrophotometric method for determination of amount of paracetamols in various drug formula. And also our method is carried out based on the oxidative coupling reaction, which is very simple reaction with the methyl dopa, which also methyl dopa is it's type of also drug is used for the high pressure drug in the presence of dissolved oxygen, which means we don't need any oxidized agent, which almost that very toxic chemical compound. In our experiment, we use the like dissolved oxygen or the oxygen that has been dissolved in water to oxidize our compound. And also our experiment we don't need like control the temperature or using solvent extractions step to calculate. Therefore, like we developed a very simple, accurate spectrophotometric method for determining very common drug, which is paracetamol. Thank you for your attention.